Have you ever stopped and wondered why Go seems to be the engine behind, well, pretty much the entire modern DevOps world? Today, we're going to dive deep into exactly that, from its core design choices all the way up to the high-level patterns that let us build powerful and, maybe more importantly, safe automation. So let's just start with the big question right up front. Why is this one language so incredibly dominant in this space? I mean, when you look at the absolute titans of cloud-native infrastructure, we're talking Kubernetes, Terraform, Prometheus. They all share the same Go DNA. Understanding why that is pretty much the key to understanding modern operations. All right, first up, the premise. Let's break down what makes Go such a ridiculously compelling choice for anyone working in operations.
So, the whole case for Go, which is championed by folks from places like Google and Microsoft, really just boils down to these four core pillars. Safe, it's fast, it handles doing lots of things at once, and it's simple to read. But, of all these advantages, there is one that infrastructure engineers value above pretty much anything else: safety.
And this is that safety net in action. With Go, any type errors get caught way back at compile time. That's before your code ever even thinks about running. Now, contrast that with a dynamically typed language where a mismatch might only pop up in production, causing a live failure. For the tools that manage our critical infrastructure, catching errors early isn't just a nice-to-have, it's absolutely non-negotiable. And hey, this isn't just a theoretical thing. A study of code on Rosetta Code totally backed this up, finding that Go had the fewest runtime failures of many popular languages. Now, this isn't about saying one language is better than another. It's about choosing the right tool for the job. And for building reliable ops tooling, static typing gives you an incredibly solid foundation to build on. Okay, so that's the why. Now let's get into the how. Section 2, the toolkit. How does Go actually deliver on this promise of safety and performance? Let's look at the core concepts developers are using every single day. First up, pointers. Now, I know this can be a tricky concept, but it's really key to how Go stays so efficient. So how do they work? Well, instead of copying huge chunks of data all over the place, you just pass around a pointer, which is really just an address telling the program exactly where to find the data in memory. Here's a great way to think about it. Passing a value is kind of like making a photocopy. Any changes you make to the copy don't affect the original document at all. But passing a pointer, that's like handing someone a copy of a treasure map. Both of your maps lead to the exact same treasure, so any changes made using that map affect the one true treasure. Next up is concurrency, and honestly, this is where Go just truly shines. Modern systems have to do a million things at once, and Go handles this with a few really powerful built-in tools. Go routines let you spin up thousands of these super lightweight tasks. Channels give those tasks a safe way to talk to each other, and mutexes, well, they act like a traffic cop, preventing all those tasks from colliding when they try to access the same data.
And check this out, another one of Go's built-in safety features, the defer keyword. It's awesome. You can basically tell a function, hey, I want you to run this line of code right before you exit, and I mean no matter what. It's perfect for guaranteeing that you always close a file or unlock a mutex, which prevents resource leaks even when things go completely wrong.
All right, that's enough theory. Let's move on to the workshop. Let's see how all these concepts actually come together to build practical, real-world tools that people use every day. So, when your services need to talk to each other, you've got choices. REST is familiar, it's human-readable, we get it. But for that high-performance, internal communication, gRPC is often the go-to. I mean, its efficient binary format can be up to 10 times faster, and its strictly enforced contracts just eliminate whole classes of bugs. It's a choice that really prioritizes both speed and reliability. And building command line tools, that's the bread and butter of DevOps work, right? And what's cool is that Go's ecosystem kind of scales with you. You can start super simple with os.args. As you need a bit more structure, the built-in flag package handles named options like dash verbose. But for the really powerful professional tools with complex commands and subcommands, think git commit or kubectl git pods, the community library Cobra is the undisputed king. It just gives you this robust framework right out of the box. So, we can build individual tools. Great. Now let's scale up and look at the assembly line. How we can use these tools to automate an entire infrastructure stack from the ground up. And this all revolves around the concept of infrastructure as code. So instead of clicking around in a web console to set up servers, the old way, you define everything in configuration files. This makes your entire infrastructure repeatable, testable, and version-controlled, just like your application code. It's a game changer. And Terraform, written in Go, is the perfect example of this. The workflow itself is designed for safety. After you initialize it, you run Terraform plan. This step is so crucial. It shows you exactly what it's going to create, what it's going to change, or what it's going to destroy. It gives you a chance to review everything before you commit with Terraform apply. No surprises, that's the goal.
And now, we've arrived at what might be the most critical part of this whole thing, the fail-safe. Because look, building powerful tools is one thing. Building powerful tools that don't accidentally bring your entire company down, well, that's the real challenge. Because when automation goes wrong, it can go wrong at a scale and speed that's just hard to comprehend. There's this cautionary tale from some Google SREs about an automated tool that started wiping the wrong disks. It's a stark reminder. It teaches us a lesson that is absolutely non-negotiable. You must build an emergency stop, a big red button to halt everything when it goes sideways. Another key to building safe automation is a concept called idempotency. I know, it's a fancy word for a really simple idea. An operation can be run over and over and over again, and the result will be the same as just running it once. So if you're creating a file and the file already exists, an idempotent tool just says, okay, cool, my work here is done, and moves on. This is what makes your automation safe to retry, which is essential for recovering from failure. And finally, the truly resilient tools. They combine several patterns to handle the chaos of the real world. Worried your tool might overwhelm another system? Use a rate limiter. Afraid of just hammering a service that's already failing? A circuit breaker will detect the problem and back off. And when you need to retry something that failed, exponential backoff does it intelligently, waiting a little bit longer between each attempt. You put them all together, and you get a system that can actually weather the storm. So, after all that, what's the ultimate takeaway from this explainer? Look, building fast, powerful tools is only half the battle. The other, more important half is deliberately engineering safety and resilience in from day one. Because as anyone who's ever worked in operations knows, power is great, but safe power is always better.